So, it so happens that the probability of the type 1 event alone is less than 1 by 2, right. So, probability of type 1 and type 2 together when you add, so it will be at most, it will be strictly less than 1, right. So, which essentially means that the original event from we started, the probability that none of these things happen, either this nor that happens, either this or this happens is less than 1 means both of them does not happen simultaneously, either this no type 1 no type 2 together is greater than epsilon. So, greater than 0, therefore, there is at least one outcome of that type, otherwise the probability would not have become like that, right. And what have you understood from this thing apart from the calculation? I did all the calculation to make sure. So, usually the calculation is a responsibility of the person who is doing it, and you do not have to teach the calculation, but just because it for the first time. So, I did all the calculation for you, but what did you understand from this, the entire business, right? So, what is the moral of the story? That is what usually we ask children, what is the moral of the story? The moral of the story was that it was a difficult, it is a difficult problem to construct this stuff, the kind of graphs which does not have the big graph 2 raised to k by 2 node graph, which does not have a k clique or a k independent set, right. But somehow existentially, that means we could show quickly that there exists some, right. This you will agree with me that it is very easy, except that the calculation may be new to you, but it is very easy, because we just calculated the probability of one of those events bad events happening, which we do not like happening, and the probability of the other bad event happening, and then we summed up those two probabilities together and told that the probability that either this bad event or that bad event happening is at most this, and that is happens to be less than 1 by some sequence of calculation we showed that. And then if both of the bad events one of the bad events happening, the probability is less than 1, none of the bad events will happen with probability greater than 0, right. That is why it is less than, the other thing is less than 1. Therefore, there should be a event, there should be an outcome which gives that probability to that event, right. There should be an outcome corresponding to that event. That means there is at least one graph, outcomes are graphs having this property, that is what we inferred. But now how did it happen so easily? That is the question. You might have noticed that we were just like loosely bounding things, right. The point here is that the kind of things that we are looking for is abundant. You understand? There are a lot of them, it is not just one, right, just that we cannot construct one, right. If we try to construct one, it is very difficult, we do not know how to construct it, but they are abundant, there are a lot of them. So, that is why if you randomly choose one, think intuitively, randomly choose one, we get it, right. But that means you became foolish, you blind and then blindly chose one and then you got it, but you became clever and tried to construct one, it is difficult, right. So, usually I tell this simple example to make you aware of the philosophy here. So, it is like so computer science students or something, you are given a project. So, suppose your building is near the seashore or something, and you are asked to program your robot to go and pick a sand particle from the seashore. You can see that very, what do? You just program it, it should walk down the stairs and that and all is possible, and then you walk to the seashore and pick a sand particle and come back. This is what you want to do. And then when you start programming, you do not know how to describe the sand particle to the robot, right. You do not know, maybe it's the image or something or whatever it can be, but there are all kinds of things in the seashore, right. There are balls left by the children, and then there are sticks sometimes, there are seashells, so shells of creatures, and the broken pieces of bangles, all kinds of things are there. What will this the robot go and take it? And so then the clever guy thought, I will do one thing, I will ask the robot to pick up a random thing and come back. Take something and come back, right? With randomly choose one and come back. You can be sure that he will bring a sand particle, I guess, because that is what abundantly available there, right? Mostly it's very unlikely that he will pick up one seashell or something is come back. We will do that because we are too clever, but if some blindly, if you become, you lose your all intelligence and then go pick up something, you just pick up something, you will get a sand particle, right? Like that, right? You become blind, right? You just, because the point is that there are a lot of them. If there were a lot of them, this would not have happened, right? So, and you can see the probability, you can, if you calculate, right, there will be a very good probability also. But sometimes, okay, the difficulty will come when this, the abundance reduces, right, less and less, and then we want to really pick up the correct way and all, and then we have to be more and more careful in this randomly. So, we have to avoid certain things and pick from the correct place and things like that, right. So, something like that. This is just there is nothing to do with the theory or something like that, just to make you aware of what we are doing. So, that why, but that was very good observation, that if you randomly choose something, you will get, though, but still it may be very difficult to construct it, right, explicitly tell that, okay, put something like this, put a vertex like this, then put a vertex. So, there are many things like that. Making explicitly constructing it would be difficult, but if you just throw edges randomly and ask what is the probability that you will get one, you will get a reasonable probability, and you can show that yes, there is it will happen, right. So, I hope you understood what we are up to, and now I will tell you. So, let me see how much time I have. So, a little more time, around 15 minutes. So, then I will tell you. So, this was a very basic stuff, right, how to just a calculation of the things. And then now about the techniques. So, usually we will use expectation. This is something which helps you a lot to deal with this stuff. Suppose x is a random variable, and x can be written as y plus z, where y and z are two other random variables, right. Something like, so randomly choose a set of students, right, and x is the number of students chosen, right, that is a random variable. So, now that means with each student I will go and toss a coin and decide whether I should pick the student or not, something like that, right, and then x is the set number of set. So, let y be the number of boys chosen and z be the number of girls chosen. So, x equal to y plus z, right, because the number of students chosen is either girl or boy. So, therefore, so like that. So, and then suppose x is equal to like that. So, expectation of x is expectation of y plus z, right, and you can, it so happens that it just adds up expectation. We need to prove it, but by the way, do you, okay, if you don't know what is probability, what is expectation? Do you know what is expectation? Expectation means, so suppose you have a random variable. So, here like that I choose students, suppose there are 50 students here, so I choose. So, what are the possible values x can take, right, x can be 0, right, x can be 1, x can be 2, x can be up to 50, right, if there are 50 students here. Now, you can always ask what is the probability that x equal to 0, right, there will be some probability, right, depending on how I am selecting, right. So, and then there can be a probability, what is probability that x equal to 1, you can find out, say, let us say p0, p1, like that. So, like that probability that x equal to I is equal to pi, right. Now, the expectation is this one, no, the I into the value of the random variable into probability that x equal to I, right, I equal to 0 to 50, you add up. I will say that this is the expected number of students I get, right, if I do this thing or something, expected number. So, a very loose way of telling. Sometimes this can turn out to be some fraction and all, right. So, do not take it too seriously when I say expected number of students. I sometimes expect half students to get things like that. So, so this is, but this is the formula, right. So, because we know that I student will be there with this kind of probability. So, we are finding a weighted average of that, weighting by the probability of each I coming, right. So, that is the expected number. And you will, so let us look at, so to understand expectation, let us ask this question. Now, I have this GNP, right, GNP. So, that means each edge comes with probability half, sorry, P, and it is not there with probability 1 minus P. Now, after doing this experiment, I create the graph. So, this graph is randomly chosen. What is the expected number of edges? So, number of edges is the random variable here. What is the expected number of edges? How will you write the formula for that? So, you should know the possible values of x. So, what are the possible values of x? Yeah, it can be 0, 1, 2, 3 up to n choose 2, right. So, now you may have to sum I equal to 0 to n choose 2 and I into probability that this x happens to be equal to I. That means, the probability that the graph is selected has exactly I vertices, we should know, and then sum by the I, right. This seems to be a little tough, right, the formula, this is from the basic definition of the expectation. So, what I am going to tell now is how to deal with this in a much easier way using the so called linearity of expectation. So, the point is that if a random variable x can be written as two other or many other random variables, say x1 plus x2 plus some xk, then if you want to find the expectation of x, you can find the expectation of the individual things and sum up. So, this also requires a proof, but I skip that. It's not a very difficult thing at all. So, there's no hyping about it. It's just that in principle it is like you sum over the rows or write a matrix or something, sum over the rows and sum over the columns, both are equal or something like that. But you can try to reproduce it yourself, right? Or I am telling in the discrete case, right? I skip the proof. Anyway, we have some very little time. And so, now let us look at how to find x equal to the number of edges, right. So, edges. What I do is I define something called an indicator random variable corresponding to each edge, for each edge, each possible edge means each pair of vertices. So, I can, there are m edges, right. So, then I can, the first edge, so xe1, xe2, like that xem, I can define an indicator random variable. This indicator random variable will take only two possible values, namely 1 or 0. If it takes 1, that means that edge appears, otherwise it is 0. It indicates whether the edge is there or not. Now, you know this x is equal to sigma of this xei's, right, I equal to 1 to m. Because if it is 0, it is not counting that edge. If it is 1, it is counting that edge, right. Now, when you want to find the expectation here, you can find the expectation of individual things and sum. That is the power of the linearity of expectation, because now it is very easy to do, right. because for that indicator random variable finding the expectation is very easy. Why? Because there are only two possible values it is taking. The two, one of them is 0. So, you do not, the summation is not complicated, right. 0 into something you can forget, 1 into something only you have to worry. What was that 1 into something? The probability with 1 occurs. What is that? The xc will be set to 1 when that edge appears, and that edge appears when the coin tossed gives a head there. That means p is the probability. So, for each of these things will be the probability will be p, right. So, it is just that m times p will be the, sorry, m means what? M is n choose 2, right, n choose 2 times p. So, n choose 2 times p will be the expected number of edges then, right. Okay. So, this just told to make you aware of how to use this independent, sorry. So, now I will ask one question. What is the expected number of triangles in the randomly chosen graph here, GNP model, GNP distribution? Triangles means triangles. How many triangles are there? How many possible triangles are there first of all? N choose? N choose 3 possible triangles are there. Now, for each possible triangle, you assign an indicator random variable, put value 1 if it appears, otherwise 0. And what is the probability that that indicator random variable will be set? That means that triangle will come. P cube, P into P into P, all the 3 edges should appear, no? Right. P cube. So, P cube into 1 plus 0 into something, I do not care, right. That is the good thing about 0, you do not have to worry about where it is. So, P cube, right. So, this indicator random variable trick is very nice because of that, I only have to calculate that. So, P cube and sum over all possible triangles, namely n choose 3, right, n choose 3 into P cube, that would be the expected number of triangles. So, this is the moral of the story here is that expectation in many cases can be found out very easily, in spite of the fact that that other formula was very clumsy, right, because we can use the linearity of expectation and the concept of indicator random variables. Just that we have to understand what is like this. For instance, my first thing, I was tossing a coin with probability p on each student here, right, and taking the student in my, so collecting or asking the student to come to the stage if the head was turning up. Then how many students, what is the expected number of students I will be getting then? Right, no, it is easy. So, otherwise it will be a little clumsy. So, this is one basic idea, and then this using this thing you can this thing. I was thinking that I can do a very simple stuff. I do not know if what is the next idea, the next thing? It is okay. I still have around 6 minutes. Let me quickly try to do that. It may be a little too fast. So, we will show that how big an independent set do we have in a graph? Graph on n vertices and average degree d. If average degree is d, how many edges are there? N into d by 2, because the total sum of degree will be then n times d and n d by 2, right. This many edges and this many vertices. Now, how big an independent set can I find, right? The strategy is this. I will, like the way I picked up students here, I will pick up the vertices thinking that I will get an independent set, right. And if I suppose I get independent, suppose I get, right, then I can find the expected number of vertices in that independent set, and that means I expect to get this many vertices in the independent set. But one good thing about expectation is that there should be at least one outcome with an independent set having that many, because otherwise that's also coming from the formula, because expectation is written like that, right? Probability into the value, this thing. If all probabilities were, all the non-zero probabilities above that expectation value, then that will sum up to more than that, right? That formula. So that if you go back to the expectation formula, you will see that if the expectation is some k for a random variable x, then in at least one outcome, for at least one outcome, probability x should take the value k or less, and similarly some outcome it should take value k or more, right. So otherwise, if all values were greater than k, right, then probability of into something greater than k plus probability of something greater than k, like that only will come, no. So then if you sum up those things, because probability sum up to 1, so that will disappear, something greater than k only will come. Then how did the expectation become x? So go back to the basic formula of expectation. So therefore, the good thing is just show that the expectation is certain value, then we are sure that there exists some selection, right, with the value equaling to it or less than that or more than that, something like that, right. This is the basic idea, expectation argument. And for instance, when I say that the number of edges, the expected number of edges is n choose 2 into p, that means that there exists some graphs with n choose 2 into p edges, that is there, right, we know. Similarly, when I say that the number of triangles in the randomly chosen graph is n choose 3 into p cube, we know that there exists some graphs with at least n choose 3 into p cube number of triangles in it, right. So the same idea we will use in the case of independent set. What I am doing is I just pick up the vertices with the probability p. So then, like the student's case, so n into p will be the expected number of things which I picked up. So x being the set of vertices randomly picked, the cardinality of that, right, sorry, the cardinality of that x. Now the only problem is this may not be an independent set, right, otherwise I could have told that np sized independent set exists, right. No, it is not true, because this may not be an independent, you just randomly picked up some vertices, there can be edges inside that. So then you ask, how many edges are expected in the picked set, selected set? How many edges are expected in the selected set? How many edges are expected? So for example, if an edge uv has to be there, both u and v should be picked up, no? So what is the probability that both u and v are picked up? Because they are independent coin tosses, right. So therefore, p with p probability this will be picked up, with p probability this will be picked up. So p square probability this edge can come, right, both has to come, right. And then what is the expected number of edges? Same idea of indicator random variable, right, every edge gets an indicator random whether it comes or not, and that comes with probability p square. So n into d by 2 into p square is the number of edges in the selected set. Let us say y is the number of edges in the selected set, right. Now what we are looking for is to get, we will define, this is the trick, we will define some new random variable x minus y, right. X minus y means the number of vertices selected and minus the number of edges. It can become negative number, positive number, whatsoever, but I will see what is the expected number of that, right. So expectation of x minus y. So by linearity of expectation, this is very easy, like expectation of x minus expectation of y. So we know both of this is np minus n d by 2 into p square. Now if put p equal to 1 by d here, that is up to me, right, because I could have decided that. So, this p square will become 1 by d square here, what 1 d will be cancelled from above, and this will be n by d here minus n by 2 d here. So, n by 2 d, right. So, there exists a selection of vertices when you do this picking up x sets, such that this x minus y, the random variable x minus y will evaluate to the expectation is that, right, for that x minus. So, there should be a selection where the value of x minus y is actually n minus d n by 2 d or more, n by t or 2 d or more. So, that is good. Then what you do is you take that selection, and you know the number of edges is only that much then, right. So, you destroy all those number of edges by removing one endpoint of those edge. So, what is left is x minus y, right, because y things will be destroyed, y vertices will be removed from x. So, x minus y will be removed, will remain anyway, and but expected we know that that selection was such that it had x minus y equal to n by d 2. So, the remaining is an independent set, right. So, we get an independent set of cardinality at least n by 2 d. Yeah, this was a little quick, but I just wanted to tell that you can it is a clever way to do certain things. So, this simple application of linearity of expectation only.